read through in going from state P to Q. It's read the substring, input string, X, okay, for any width. So that's sort of the big picture. If you can get that, you're halfway there. Okay. Now we just need the details. All right. Okay. So X is your substring going into the PDA, right? And this variable is to generate X. That's what we need to do. Okay. And this X is a substring that the PDA, starting in state little p and ending in state little q, when it reads X. So you want the grammar. Remember, we're trying to construct a grammar that behaves like the PDA. So you want the grammar with this variable to generate that substring X. All right. Now, one of the basic assumptions in the model, this construction, building the grammar, is for every possible pair of states. What states? Well, all the states P and Q, the states of the PDA, right? Grammars don't have states. Right? They have variables and rule, substitution rules, and a set of terminals. And, it's different worlds, but you can make the one behave like the other, and vice versa. That's the whole point of this big theorem, right? So we want this variable to generate that substring. Okay? Grammar, PDA, but it's the same substring. It's the substring that gets generated by the grammar, and it's the same substring that gets read by the PDA, and the PDA goes through from state little p to state q. Okay. Right. So we set up let's say the PDA has big N states, different states. So into the grammar we will put n squared variables. Right? We'll have a variable for every pair. Ordered pair? Yeah, I think ordered pair. Is that true? I hadn't thought about that. I guess ordered pair. So APQ would be different from AQP. So there will be n squared variables in your grammar, call it big G, grammar G that you're generating. Okay. So we got the stage last time. I'm just writing it out a bit again here. We have to prove this particular claim. So if this variable generates this substring, then X will take now big P is just the PDA. Big P for PDA. It's the label for the PDA, and big G is the label for the grammar. Okay, so that substring X, that will take your machine, your PDA, from state P with an empty stack. Extra detail. Okay, the empty stack it's useful. We need it. It makes the proof go much easier. Well, relatively easier. Okay. So reading when the PDA reads this X, this substring, it starting in state P, it'll end up in state Q, and with both states having an empty stack, right? At the start reading time and the end reading time of that substring, as the substring goes into the PDA. Right, and we're going to prove this by induction, and typically induction involves some kind of integer. And in this case, what's the integer? Well, it's the number of steps in the derivation of X from this variable. Now, derivation, what does that mean again? Bit of a refresher. You derive a string from a variable by using substitution rules. So you start. Let's say you start with a. Well, let's go start at the beginning. You start with a start variable, big S, capital S, and then you apply successively substitution rules. So you look at your intermediate string, and you find a variable, and you find a rule whose left-hand side matches the variable that you're going to substitute. Then you throw out that variable and you replace it by the right-hand side of what's in the rule, the substitution rule. So you substitute what's on the right, well, you're on the right-hand side of your rule for the variable in the intermediate string. And you keep doing that until eventually you get a string full of terminals. And that process of substituting, that's called deriving. Okay? So from the grammar you derive a string. Okay? So how many steps, like starting from a given intermediate string, how many steps do you take? Like how many substitutions, in other words? How many applications of a substitution rule do you need to get to your final string? Okay? So that'll be an integer, of course, positive integer, number of, or 0, a non-negative integer. So that's the integer we're talking about in this induction proof. Okay. All right. So using all the model, all the rules we have in the grammar, and actually I could have put this first. This here are all the rules that you put into your grammar to make it work. So you've seen this before, but I put it here again. But perhaps I should have put it here and then refresh first. But well, it doesn't matter too much. So using the rules here, we can actually show that the PDA will, starting in state little p with empty stack, it'll end up in state Q with empty stack, being derived, that x being derived from this variable. That's what we have to show. Okay. Hold on. What are we saying? So you're told this variable generates x. Okay. So x is derived from this variable, right? And that being the case, then we have to show that the same x, the substring, in the PDA will take the machine from state P with empty stack to state Q with empty stack, and we'll prove it by induction. And the integer involved in this induction is the number of steps in the derivation from this to that. Okay. All right. Well, it's an induction proof. 2 steps as usual. The basis step, you prove it for some very low number, usually 1 or 0, usually. And then the inductive step, which is here, you assume it's true. Whatever it is you're trying to prove, you assume it's true for, I don't know, k something, integer k, and then prove that it's true for k plus 1, and then you've proved the whole thing. Because if you've proved it, say, for k equals 1, and you've also proved if it's true for k, it's true for k plus 1. So if it's true for 1, it's true for 2, and if it's true for 2, it's true for 3, and so on. So it goes up infinitely. So you've got the proof. All right. So let's try to prove this. One step. Okay. Now, before getting into, let me refresh. To make this proof, we will make use of the rules in the grammar. And where did those, what rules? The substitution rules. Where did these rules come from? So now, the rules that you put into the grammar that's the creativity of the proof. You know, whoever dreamt this up, I admire, because it's quite an ingenious proof. So the rules that got put into the grammar are put there to enable the proof to work, to enable the grammar to behave like a PDA. It's you know, it's a complicated proof, but quite ingenious. You know, once it clicked, I hope you have that and now I get it. Okay, you know, I hope you have that experience, because it's quite an ingenious proof. All right. Okay, so we're talking about now we're constructing the grammar. We're constructing its states and its rules, its substitution rules. Okay, and I can tell you what they are. And you've seen this before on the previous board, but they probably were relatively meaningless. But now we're actually getting into the proofs. You'll be able to, in fact I suggest, go back and forth between the proof and these rules, because the rules are a function of the proof. You know, they're there to enable the proof, and what you want to prove motivates the choice of the rules that you put into your big R in your grammar, you know, the substitution rules. So the two are closely linked. So I suggest, you know, go back and forth to see, you know, why one set influences the other, and it's a two-way street. So okay. So firstly, the set of states, that would be your, you know, we're talking about a grammar, right? So that would be big V, the set of states. And the suggestion is, now I have a variable that will take you from any state to any other state in your machine. And big Q here, remember, is just a set of states of the automaton. Okay. So if you have n different states here, you'll have n squared of these variables, and assume yeah, PQ is different from QP. That would make sense. All right. Now let the start variable be this. Now why is that plausible? Now Q0 is the initial state of your machine, of your automaton, and Q accept is well, that's an accept state of your automaton. Now it's A of, you know, these two states. Now, oh, by the way, these states, look, variables. What's their function? You know,